Hello, a little bit more about magnets. This time we'll look at induced magnetism. So we have here on the left, we have two permanent magnets. Okay, they are magnets all the time. On the right here, sorry, we have some nails and some of these bits of metal here and some paper clips, which are not magnets. Okay, these are attracting each other. These magnets are attracting each other. But these paper clips, the nails, they are not attracting each other or repelling each other or doing anything. But we already saw that they are magnetic. We can pick them up with a magnet. So how does that work? Okay, let's try something. This piece of metal, okay, this is actually iron. Well, it might not be iron. It might be something that's similar to iron that they've made as an alloy, but it's very magnetic. But it's not a magnet. Okay, this is not picking up this other one. If I attach it to this magnet, this now will pick up the other piece of metal, and that other piece of metal will pick up a paper clip, which will then pick up more paper clips like that. But if I take the magnet away, suddenly everything falls apart. So it stops being a magnet. It's as if this temporarily becomes a magnet while it's attached to the magnet, and then when you take the magnet away, it stops being a magnet. And that's exactly what happens. What we say is that this piece of iron has magnetism induced in it by the magnet. So this is a permanent magnet. It induces magnetism in this piece of iron. So effectively it temporarily makes this into another magnet. Which way round will that be? Well, whichever end is attached to the North Pole, it's attracting it, so it must be a South Pole. So it must be making this temporarily a South Pole. So I'm going to put it in pencil. No, I'll put it in pen. I'll put it in pen, but I'll rub it out. That's a South Pole, and that's a North Pole, but it's only temporary. So as soon as I take the magnet away, let's just pick something up with it. Let's pick up one of those nails. Okay, when I take the magnet away, it loses its magnetism, so this south and north disappear. Okay, and then if I put it around the other way, it will create a north pole next to the south pole and a south pole at this end, and that will pick things up. Okay, but that is again temporary, and as soon as I take that away, it drops. Now some things actually stay a little bit magnetized when you connect them. So this iron nail, actually, it will pick things up like that, but it's probably a steel nail actually. And when I take the magnet away, it actually stays a little bit magnetic. Okay, it does actually start to pick things up. So it doesn't completely lose its magnetism. It actually does retain some of its magnetism. Okay, but it's much weaker than a normal magnet. Now, I said that we get a south pole at one end. I'm getting all tangled up. Everything's attracting. Okay, I said that when we connect this to the magnet, we'll get a south pole here and a north pole here. If that's correct, then if this is the north pole, it should repel from another north pole. So let's see if it does do that. And let's see. Maybe, yes. Okay, if I get it so that it will repel. Oh, see, it's sticking there, but it's not. Yes, it's repelling there. It depends on whether it can actually move and repel. I can also show the same effect with a piece of nail, or one of the nails. Okay, this nail can actually swivel on here. If I get a north pole here, that means this will be a south pole, which means that must be a north pole. If I take the north pole here, it should repel that end of the nail, and it does. But if I take this magnet away, this stops being a magnet and just attracts, so it's magnetic. Okay, so what we say is that we have induced magnetism temporarily. So how does that happen? Let's have a look. I'm going to sweep this out of the way. There we go. Well, if we were able to look inside this piece of metal like that, we can visualize it as if it has areas or regions within it which are themselves slightly magnetic, magnetized rather, and they have magnetic direction where they are magnetized in different directions, like that. Okay, so we'd have arrows pointing in the different directions that they're magnetized, north to south, whatever, or south to north. And in the piece of metal, normally they're all randomly arranged. So when there's no magnet near it, the direction of all the different areas within the magnet are all at random orientations, so they cancel out. So there is no overall magnetic effect. Okay, so it's not magnetized. If, however, we bring a magnet near to it, okay, so like this, okay, then what happens is this is our piece of iron, and here's the magnet. I'm going to say this is north. Is it north? Okay, I'll turn it around. Okay, it's south, north. Okay, there's north and there's south of my big magnet. Okay, I'm going to draw an arrow pointing this way because that's where pointing north would be. What that does is it takes each of these little regions within this piece of iron and it attracts them, and it basically reorientates them so that they are all rearranged to face the same way, like that. And because they're all rearranged to face the same way, the magnetism of each little domain, each region, reinforces, and so they produce an overall effect. So magnetism of each domain reinforces to make it a magnet. I can't spell. Magnet, M-A-G-N-E-T. I don't know why I couldn't spell there. Okay, pretend that never happened. Okay, so it temporarily rearranges the direction of magnetism of all the little domains within this piece of iron, and when you take the magnet away, they just revert back to their original random orientation. So we say that this has temporarily induced magnetism in the iron. Okay, so this is the magnet, this is the iron. And that's how induced magnetism happens. It turns this into a small magnet. It's as if this is a south and a north. Okay, so this can then attract another magnet or another piece of iron or something on the end, like that, and like that. Okay, so that's induced magnetism.